Good morning, all of you. Welcome to Sri Jayendra Ag Zone. In the previous session, we have discussed about various theories of acid, bases, and salts. Now, in this session, we are going to discuss about ionic product of water and questions based on ionic product of water as well as acid, base, and salts. So, please listen carefully. It's very, very important. Now, we are going to start new topic in this chapter, ionic equilibrium. In the first lecture, we have completed already various theories of acids and bases and salts. Various theories of acids, bases, and salts. Now, in this session, we are going to discuss new topic, that is degree of dissociation of acid. When an electrolyte is dissolved in a solvent like water, it spontaneously dissociates into ions. It may dissociate partially or sometimes completely. Partially in the case of weak electrolytes and completely in the case of strong electrolytes. Partially in the case of weak electrolytes, as we have already seen in the first lecture, and completely in the case of strong electrolytes. In the case of strong electrolytes, they go complete dissociation, strong electrolytes. So what are weak electrolytes, what are strong electrolytes, we have discussed in lecture 1. So you can see that. Now, NaCl is a strong electrolyte. It dissociates in water to form Na plus and Cl minus. Along with water, it can form equilibrium. Whereas acetic acid, when dissociates in water, it forms acetate ions as well as H plus ions. So when an electrolyte is dissolved in a solvent, so in this case, alpha is equal to almost 1, and in this case, alpha is less than 1. So weak electrolytes dissociate partially, whereas strong electrolytes dissociate completely. That's why this reversible reaction is not applicable in case of strong electrolytes like NaCl, whereas for weak electrolytes, it is applicable because ionic equilibrium is nothing but the equilibrium attained between the weak electrolyte and its ions in the aqueous solution is nothing but ionic equilibrium. So ionic equilibrium will be existing for weak electrolytes only. For strong electrolytes, it is completely dissociated, so the alpha is equal to 1. Next, continuation. The degree of dissociation of an electrolyte alpha is a fraction of 1 mole of the electrolyte that has dissociated under the given conditions. Example, alpha is equal to number of moles dissociated by number of moles taken initially. So number of moles dissociated by number of moles taken initially. The value of alpha depends. This they'll ask in the competitive exams. What is the nature of alpha depends upon. Alpha depends upon first one, nature of electrolyte. Strong electrolyte dissociate completely, whereas weak electrolytes dissociate partially. So all strong electrolytes dissociate completely, 100% addition. That's why their value is taken as alpha is equal to 1. And weak electrolytes dissociates partially. So the factors affecting alpha is, first one is nature of electrolyte. Nature of electrolyte, strong electrolytes dissociate completely, whereas weak electrolytes dissociates partially. Now, second factor, nature of solvent. A solvent having high value of dielectric constant like water. Water is having high value of dielectric constant, will favor dissociation. Next, third one, dilution. For weak electrolytes, degree of dissociation increases by dilution. This is called Ostwald's dilution law. Very, very important. What is Ostwald's dilution law? For weak electrolytes, degree of dissociation alpha increases by dilution. So the further dissociation of weak electrolyte will be increased by diluting the solution. So this is called Ostwald's dilution law, which we are going to discuss in the next. Next, temperature. On increasing temperature, generally degree of dissociation also increases. With the increase of temperature, degree of dissociation also increases. What is degree of dissociation? Denoted by the letter alpha. Next, continuation. Presence of other solute. When a substance is present, it may affect the solubility of another solute. Generally, presence of common ions suppresses the degree of dissociation of a weak electrolyte. Let me explain this example. For example, now here, acetic acid along with water is there. When acetic acid is dissolved in water, it forms acetate ions plus H plus ions. And for this solution, if you add, sodium acetate, then what happens? It further dissociates to form CHCCO minus and Na plus. This CHCCO minus combines with H plus and finally get back to acetic acid. So, due to the common ion, that is acetate ion, due to the common ion acetate ion, the suppression of acetic acid is being, acetic acid dissociation can be suppressed. The dissociation degree of the dissociation of acetic acid can be suppressed by adding sodium acetate to the solution. So, this is called common ion effect. What is this called? Common ion effect. So to suppress the degree of dissociation of weak electrolytes such as acetic acid, if you add small amount of sodium acetate, it will suppress the further dissociation of acetic acid because from sodium acetate it forms again sodium acetate ion and sodium ion. Due to this, what happens? This acetate ion combines with H plus ion of the first case, then they form again acetic acid again. So due to this, what happens? The suppression of acid gets dissociation, and the acid's dissociation is being suppressed. This is called common ion effect. So what is the fifth factor? When a substance is present, it may affect the solubility of another solute. Generally, presence of common ion suppresses degree of dissociation of weak electrolyte. So due to the presence of common ion, it may not dissociate into ions because again it is forming acetic acid in this case example. So that is why this is called fifth topic. So fifth factor. So these are the factors affecting degree of dissociation. First one is nature of electrolytes. Second one is nature of solvent. Third one is effect of temperature. Fourth one is presence of other solute and effect of dilution. Fifth one is effect of dilution. So all these five factors are very important. So which will affect the alpha value? Alpha is affected by nature of solvent, nature of solvent. Second one, nature of electrolytes. Third one, effect of dilution. Fourth one, effect of temperature. And fifth one, presence of other solute. So the presence of other solute, if the other solute contains common ion, which is with reference to the weak electrolyte, then it will suppress the dissociation of the weak electrolyte. So to suppress the dissociation of weak electrolyte, we can add a substance in which it contains common ion. Hence, it is also called as common ion effect. Common ion effect. So these are the five factors affecting alpha. Note down in your classwork. Next continuation. Now, what is Ostwald's dilution law? For a weak electrolyte such as A plus B minus, when dissolved in water, if alpha is a degree of dissociation, then initially A is full with concentration C, and as there is no formation of A plus and B minus initially, and after at equilibrium, what happens? This becomes C into 1 minus alpha, this becomes C alpha, and this becomes C alpha. So then according to law of mass action, equilibrium constant K is equal to concentration of products by concentration of reactants. So concentration of products is C alpha into C alpha, and for concentration of reactant, that is AB, is nothing but C into 1 minus alpha. So on the whole, it becomes C alpha square by 1 minus alpha, which is called dissociation constant of weak electrolyte. So the same thing we can write dissociation constant of acid also. If you take weak electrolyte as acid, then degree of dissociation of acid Ka is equal to C alpha square by 1 minus alpha. This formula is very, very important, where alpha is called degree of dissociation, C is called concentration of the solution. C is called concentration of the solution, that is equal to molarity. So C is called concentration, alpha is called degree of dissociation, and Ka is called dissociation constant of weak electrolyte. Here in this case, I have taken acid. So Ka is called dissociation constant of acid. Kb is called dissociation constant of base. So on the whole, for weak electrolyte, K equivalent is equal to concentration of A plus into concentration of, that is concentration of products by concentration of reactants. Here the product is A plus and B minus, and reactant is concentration of AB. So by this we can say, since concentration of A plus is given as C alpha at equilibrium is observed, and B minus also C alpha is observed. So C alpha into C alpha by C into 1 minus alpha, because this is decreasing. How many times it is decreasing? C into 1 minus alpha. So that's why you can say C alpha square by 1 minus alpha is called Ka value. or K equivalent value, or you can say Kb value. So in case of acid, it is Ka, and in case of base, it is Kb. Kb is equal to also C alpha square by 1 minus alpha. This is called dissociation constant of base. Dissociation constant of base. So please note down, and this is the formula for finding dissociation constant of weak electrolyte. On the whole, electrolyte can be an acid or base or salt. So that's why you can say on the whole it is called K. K equivalent is called dissociation constant of the weak electrolyte, and it is equal to C alpha square by 1 minus alpha, where alpha is called degree of dissociation and C is called concentration. Next continuation. So C is equal to 1 by V for 1 mole of a 1 molarity solution. We can say volume of solution in which 1 mole is present. So we can say alpha square by 1 minus alpha into V, because C is equal to 1 by, because molarity is equal to, what is C? C is called molarity. Molarity is equal to number of moles by volume of solution liters. So if number of moles is equal to 1, volume of solution liters, so we can say C is equal to 1 by V, because if we take 1 mole, 1 by V, so we have taken 1 by V. If alpha is negligible in comparison to unity, then 1 minus alpha is almost equal to 1. So we can write K equivalent is equal to alpha square C, or alpha is equal to root of K equivalent by C, or K equivalent into V, because 1 by C is equal to V. So by this we can say alpha is proportional to 1 by concentration. This is called thumb rule. Very, very important, these formulas. So K is equal to C alpha square, or implies alpha is equal to root of K by C. Where C is called concentration of the solution, K is called dissociation constant of acid, base, or salt. That's why on the whole we'll say commonly K equivalent. K equilibrium, or alpha is also equal to, we can write root of K equivalent into C, because since 1 by C is equal to 1 V, so into V if they have given volume. So all these three formulas are very, very important. Please note down. When can you neglect 1 minus alpha? For weak electrolytes, 1 minus alpha is neglected. If alpha is negligible in comparison to unity, that is 1 minus alpha is similar to 1. So we can say alpha is proportional to 1 by concentration. So for weak electrolytes, 1 minus alpha is neglected, because it is almost equal to 1. So that's why we can say K is equal to C alpha square. That is K equivalent. K equivalent means equilibrium constant of electrolyte. K equivalent is equal to C alpha square. So all these three formulas are important for objective. Please note down. Next. As the concentration increases, alpha decreases. By this, what we understand, since alpha is proportional to 1 by concentration, as the concentration of the solution increases, alpha value decreases. At infinite dilution, alpha reaches its maximum value, and it is called as unity. Its value is taken as unity, that is equal to 1. So this is 0.1 alpha, and here if we take into consideration, so 0.121. So this is the decrease of concentration of the solution. As alpha increases, concentration of solution decreases. As the concentration increases, alpha value decreases like this. This is the graph related to C and alpha. Alpha is called degree of dissociation and C is called concentration. As the concentration increases, alpha value decreases. Next, ionization constant of weak acid and weak base. Ionization constant of weak acid and weak base, that is Ka, as I told you, for weak acid. So now consider an acid, weak acid plus water, it forms H3O plus and A minus. Here Ha is called acid, H2O is called base, H3O plus is called conjugate acid, and A minus is called conjugate base. Applying law of chemical equilibrium, K is equal to concentration of H3O plus into concentration of A minus by concentration of Ha into concentration of H2O. Since concentration of water is very, very large and remains almost constant in solution, it can be combined with K to give another constant Ka. So this water, it is combined with K and forms K of water, which is equal to concentration of H2O plus into A minus by concentration of Ha. And for this, by this, you can say Ka, ionization constant of weak acid, is equal to concentration of H3O plus by A into A minus into concentration of Ha. So this is called ionization constant of acid. This is called what? ionization constant of acid. For example, if we take acetic acid ionization constant of acetic acid, Ka is equal to concentration of CH3CO minus into concentration of H plus divided by concentration of CH3COH, that is acetic acid, weak electrolyte. So in this way, we'll find out the value of ionization constant of acid. Ka is called dissociation constant of acid or ionization constant of acid. Both are similar. Next, similarly, we can find ionization constant of base also. So since water concentration is very, very large, it is taken as 1. So this is called as Ka, where Ka is called ionization constant of acid. Very, very important. Please note down. So for example, I have given ionization constant of acetic acid. It's been calculated by using the formula. Acetic acid dissociates to form acetate ions and H plus ions. So ionization constant of acetic acid is equal to concentration of CH3COO minus into concentration of H plus by concentration of CH3COOH. That is called acetic acid. Next continuation. The value of ionization constant gives an idea about the relative strength of acid. Larger the value of Ka, this sentence is very, very important. They will give which are the following in the decreasing order of their acidic strength. Arrange the following in the decreasing order of their acidic strength, and they'll give Ka values of all acids. And in that case, what we have to keep the first one. Larger the value of Ka, higher is the concentration of H3O plus ions and stronger is the acid. If dissociation constant of two acids are known, their relative strength can be predicted. For example, the dissociation constant of acetic acid is being considered as H3O plus into CH3CO minus by CH3COOH, which is equal to 1.8 10 to the power minus 5 at 298 Kelvin. This is the value which is calculated. So from this statement, very definitely they'll ask question from this statement. They will give dissociation constant values of A, B, C, and D, that is Ka values, and they ask us to write and the following in the decreasing order of the acidic strength. So larger the value, further what is the answer? Larger the value of Ka, higher is the concentration of H2O plus, and stronger is the acid. So this statement is very, very important. Please note it down in the classwork. Again, I'm repeating the statement. Larger the value of Ka, higher is the concentration of H2O plus, and stronger is the acid. So if the dissociation constant of two acids are known, we can find out the relative strength can be predicted. For example, you can see here, Ka values of A, B, C, D will be given. Ka value of acid A is equal to say 1.2 in 10 to the power of minus 5, and Ka value of acid B is equal to 1.6 in 10 to the power of minus 6, and Ka value of similar Ka value of base, sorry, some other acid is given as 2.8 in 10 to the power of minus 6, and D value, Ka value for acid D is equal to 2.8 in 10 to the power of minus 5. So if they ask us, they are in the following in the decreasing order of the acidic strength, because they have given Ka values of A, B, C, and D. So by using these values, 10 to the power of minus 6 and 10 to the power of minus 5. So minus values you should not you should neglect. Only the powers only we have to consider. So this is highest, and first you have this one, next second. So C is greater than B, B is greater than D, and D is greater than A. So answer is C, B, D, A. So like these questions you may expect for in competitive exams, entrance exams. So that's why this statement is very important. Don't forget this statement. Larger the value of Ka, higher is the concentration of H3O plus, and stronger is the acid. So which one is having highest power? So that is having larger value of Ka. That is ionization constant of acid. What is Ka? Ionization constant of acid. Next continuation. So, for example, hydrogen fluoride, Ka is equal to H3O plus. How we got this H3O plus? For example, I'll show you. HF, when dissociated in water, since HF is acid, it changes to H3O plus ions and F minus ions. F minus ions. So these two becomes products and this becomes reactant. And the reactant will not consider concentration of water because it is taken as unity. So by this we can write K of HF is equal to concentration of H3O plus into concentration of F minus by concentration of HF. And its value is observed as 6.7 in 10 to the power of minus 4 at 298 kelvins. So since KHF is greater than CHCOH, therefore HF is stronger acid than CHCOH. HF is stronger than CHCOH. So higher the value of Ka, stronger is the acidic. And this is in the power of 10 to the power of minus 4, that is 10 to the power of minus 6. So minus values you have to consider. So definitely you have to do minus values, you have to consider, and you'll get the answer like this. So the statement is simple statement. Higher the value of Ka, stronger is the acid. Higher the value of Ka, stronger is the acid. That's all simple because Ka is proportional to H3O plus ions. So please note down this. You can understand easily. So these type of questions are important. Anyway, at the end of this lecture, we are going to do these type of questions. Next, relation between dissociation constant and degree of dissociation. What is the relation between Ka and Kb? So consider weak acid which is not dissociated to 100%. Let us say weak acid is Ha. Initial concentration is C at time is equal to 0. And initially, as there is no formation of products, we can say H plus and A minus becomes 0, 0. And at equilibrium, what happens? This becomes C into 1 minus alpha and C alpha and C alpha. So this becomes C into 1 minus alpha and C alpha and C alpha. So now Ka is equal to concentration of H plus into concentration of A minus, that is product, by concentration of reactant, that is concentration of Ha. So which is equal to C alpha into C alpha, that is C alpha square, by C into 1 minus alpha. So C into 1 minus alpha, that C and C gets cancelled. So finally, you will get C alpha square by 1 minus alpha. You can see this step simply. You can write C alpha into C alpha by C into 1 minus alpha. So this C will get cancelled. So this becomes C alpha square by 1 minus alpha. So it becomes equally C alpha square by 1 minus alpha. So this is called dissociation constant of acid or ionization constant of acid. So if alpha is less than 1, then 1 minus alpha is equal to 1. So we can say Ka is equal to simply C alpha square. So for weak electrolyte, since alpha is less than 1, then we can say 1 minus alpha is equal to almost equal to 1. So by this we can write dissociation constant of weak acid Ka is equal to C alpha square. By this we can write alpha is equal to root of Ka by C, where C is called concentration. So please note down this formula, same like electrolyte. There we have given in the previous slides electrolyte. Now we are giving exclusively for dissociation constant of acid. Anyway, we are going to do numericals based on this. So please note it down. Next continuation. Then Ka is equal to C alpha square implies alpha is equal to root of Ka by C is valid for alpha is less than 0.1 or 10%. Simply for weak base like ammonium hydroxide, we'll take it as Kb, and Kb is also equal to C alpha square. By this, you can write alpha is equal to Kb by C. So if they are given base, it's nothing but Kb will write. If they are given acid, we'll write Ka. What is Ka? Ka is called dissociation constant of acid, and Kb is called dissociation constant of base. So what is Kb here? So I'll write here Kb is equal to dissociation constant of base. So please note down all these things. Very, very important. These formulas you have to remember. This is the second topic in this chapter, that is ionic equilibrium. Very, very important chapter. Definitely you are going to get 2-3 MCQs in competitive exams. Next, we'll see what is ionic product of water. So ionic product of water, the conductivity of the measurements of water indicate that water is a weak electrolyte because water also dissociates to form H plus and OH minus in aqueous, dissociates to form H plus and OH minus. Even in pure state, water is weakly ionized to give H plus ions and OH minus ions as shown below. So the ionization constant of water may be written as Ka is equal to K alpha, that is K alpha is equal to concentration of H plus into concentration of OH minus by concentration of water, since this is taken as unity. Since concentration of water is very high, that is 55.5 moles per liter, and only a small fraction of it undergoes ionization. How we got this 55.5 moles per liter? Because that is equal to 1000 by 18. Because 18 is the molecular weight of water. So 1000 by 18, you will get 55.56. So concentration of water is very high. It is equal to 55.55 moles per liter. So by this we can say ionic product of water Ka is equal to. So therefore water may be taken as constant and may be combined with K alpha H2O to have another constant called Kw. What is this Kw is called? Where Kw is equal to ionic product of water. What is Kw? Kw is called ionic product of water. And this ionic product of water is being represented as K alpha into H2O, that is Kw is equal to concentration of H plus into concentration of OH minus. And at equilibrium, concentration of H plus is equal to concentration of OH minus, which is equal to 1 to 10 to the power of minus 7 moles per liter. It has been observed. So by this we can say Kw is equal to concentration of H3O plus and OH minus, which is equal to 1 in 10 to the power of minus 14 moles per liter square, moles square per liter square. So this value is fixed. So what is the value of Kw? 1 into 10 to the power of minus 14. Very, very important value. How we got this? Because concentration of H plus is found to be 10 to the power of minus 7 and concentration of OH minus also is equal to 10 to the power of minus 7. So by multiplying these two, we will get concentration of H plus into concentration of OH minus is equal to 10 to the power of minus 14. So by this we can say ionic product of water Kw is equal to concentration of H plus into concentration of OH minus, which is equal to 1 into 10 to the power of minus 14. Very, very important. So ionic product of water is equal to concentration of H3O plus into concentration of OH minus. So these values you have to remember because in the examination they will not give. This is at room temperature. This value is at room temperature. As the temperature increases, ionic product of water value decreases. And the degree of dissociation of water is equal to 10 to the power of minus 7 moles per liter by 55.55, which is equal to 1.8 10 to the power of minus 9. Since with the increase in temperature, that this point is also very important, please note down. Since with the increase in temperature, dissociation of water increases, therefore value of Kw also increases as the temperatures increase. However, at all temperatures, H plus ions remains constant equal to OH minus ions in pure water. So this is equal to 1.8 10 to the power of minus 16. So dissociation constant of water is equal to almost it is same. That is 1.8 10 to the power of minus 16. How it got that is 10 to the power of minus 7 into 10 to the power of minus 7 by 55.5. So it may be noted that ionization constant of water K is always equal to is different from ionic product of water. So ionization constant of water is different from ionic product of water. Why? Because ionic product of water is equal to Ka of H2O into 55.5. Ka of H2O into 55.5. This is very, very important. Please note down. These relations you will not find in textbooks. So better you copy down so that how you got ionic product of water value, you'll understand better. Next continuation. Now example 1. The degree of dissociation of pure water at 18 degrees C is found to be 1.8 10 to the power of minus 9. Final ionic product of water and its dissociation constant at 18 degrees C is. So ionic product of water Kw is equal to constant Ka of H2O into 55.5, simple direct, into 55.56. So which is equal to 1.8 in 10 to the power of minus 16 you will get. Let us see the answer now. As it's the same temperature, so moles per liter. So 55.55 into K of H2O. K of H2O is given as how much? 1.8 in 10 to the power of, that is equal to 1.8 in 10 to the power of minus 9 into 55.5, which is equal to 1.8 10 to the power of minus 16 moles per liter. So to find ionic product of water at 18 degrees C, this is the formula. What is the ionic product of water at 0 degrees C? It is equal to 298 Kelvin. It is equal to 1 into 10 to the power of minus 14. Is the value of ionic product of water at 298 kelvins. By this, what you can understand, as the temperature increases, ionic product of water also increases. Very, very important point. As the temperature increases, Kw value also increases. So please note down this in your classwork. Very, very important. Now we'll do questions based on various theories of acid and bases along with questions based on degree of dissociation in this lecture. Next, we'll go for new topic. Next continuation. So now we are going to do, I'm writing here the heading, questions. Please note down all the questions. Questions based on various theories of acids, bases, and salts. We have three theories of acid, base, and salts. And next we'll do questions based on ionic product of water also, depending on the time. Now let us see question number 1. Question number 1. So questions based on various theories of acids, base, and salts. First question. Ammonia is not a base according to option A, it is Bronsted theory. Option B, it is Lewis theory. Option C, it is Arrhenius concept, Arrhenius theory. And option D, it is Loy theory. Simple, they have given options. Both Bronsted and Loy is same only. So in this answer, directly you can say, according to Arrhenius theory, an acid is a substance which gives H plus ions when dissolved in water, and a base is a substance which gives OH minus ions. Since ammonia does not contain OH minus ions, it is not a base. So answer is Arrhenius theory. Like these questions you will get in the competitive exams. Yes, this is only basic question. Now let us see question number 2. Question number 2. CH3COOH, acetic acid, does not act as an acid in the presence of option A, it is HCl. No, they have given 4 different options. A is HCl, B is sodium carbonate, C is H2O, and D is benzene. Is benzene CCH6. So option A, all are correct. Option B, A and D are correct. Option C, A and D are correct. And option D, C and D. So the right answer is, just imagine now here we can understand. Acetic acid does not act as an acid in the presence of, so it is HCl and benzene, because HCl is itself in an acid. So answer is HCl and benzene. So the option for this answer is A and D are correct, because in the presence of sodium carbonate, it behaves as an acid, whereas in the presence of water also it behaves as an acid. But in the presence of HCl and C6H6, it does not behave as an acid, because in benzene it does not dissolve. And in HCl itself forms H plus ions, so we cannot say from where we got H plus ions. So that's why in the presence of HCl and benzene, it will not act as acid. So this is the answer. So A and D are correct. A and D are correct. Next continuation. Question number 3. So question number 3 now. In the reaction, this is very important. Question number 3. In the reaction, ammonia plus water gives rise to ammonium ion plus OH minus, ammonium ion and OH minus. The conjugate acid base pair is the conjugate acid base pair is option A, given as ammonia and water. Option B, ammonia and OH minus ions. Option C, water and NH4 plus ions. And option D, ammonium ions and ammonia. So we have 4 options straight away. Now we are going to discuss answer. Let us discuss answer now. They are asking conjugate acid base pair. So solution, I'll do it in blue ink. So first write the skeletal equation, solution for this. So ammonia combines with water. It forms ammonia plus OH minus. So straight away we can say, since here ammonia is gaining one H plus ion, so straight away we can say ammonia is called base and water is called acid here. So for water, you get conjugate base. OH minus is conjugate base. And for ammonia, NH4 plus is conjugate acid. Conjugate acid. So in this case, the conjugate acid base pairs is ammonia and ammonium ion. So answer is D, conjugate acid base pair. They are not asking conjugate acid, conjugate base. Simply they are asking conjugate acid, comma, base pair. So conjugate acid is ammonium plus and only base is ammonia. So answer is straight away D option, that is NH4 plus and NH3. Like these questions, confused questions will be given to you in the entrance exam. So this is the answer. Very, very important bit. This is simple. It is ammonia plus water. How can we identify which is base, which is acid? The substance which is giving out H plus ions is called acid, and substance which is gaining H plus ions is called base. So here water is acid because water is giving H plus ions to ammonia, and then only it is forming NH4 plus, and it is forming OH minus itself. So from water, H plus ion is going to ammonia, so it becomes conjugate acid. And so that's why ammonia is a base and water is an acid. And for base, you will get conjugate acid on the right hand side, and for acid, you will get its conjugate base on the right hand side. So this is called conjugate acid base theory proposed by Bronsted-Lowry. Very, very important. Next question. Question number 4. The conjugate acid, very important this is, the conjugate acid for the species HSO4 minus is. So option A, it is SO4 2 minus. Option B, it is H2SO4. Option C, it is HSO4 2 minus. And option D is equal to SO4 minus. So these are the 4 options. So it is very simple and it's most important question also. So with this, now I'm writing the solution in blue pen. So solution, we can see here straight away. To get conjugate acid for a given substance, to get conjugate acid for a given species, add H plus, simple. So for this, if you write now HSO4 minus plus H plus, so it becomes plus and minus become neutral, and H and H becomes H2, so it becomes H2SO4. For the same, you can write conjugate base. So HSO4 minus conjugate base is nothing but simply subtract H plus. What you have to do? Subtract H plus. So to get conjugate base. So for that, if you take HSO4 minus H plus. So this H and plus also is removed. So it becomes SO4 2 minus. So answer is second option because we have asked only conjugate acid. So the conjugate acid for the species HS4 minus is H2SO4, and for the same species conjugate base is SO4 2 minus. That's why they are given confused options also. SO4 2 minus they are given as well as H2SO4, and the right answer is H2SO4 because to get conjugate acid for a given species add H plus proton. So if you add H plus for this, you will get H2SO4. Similarly, for the given same substance, if they ask, suppose if they ask conjugate base also, and to get conjugate base for the given substance, simply subtract H plus. So HSO4 minus H plus gives H2SO4 2 minus because this H will go and minus becomes total 2 becomes 2 minus. Like these questions are most important. Definitely you are going to get in the examinations. So please listen carefully and practice like these questions. Next question number 5. I'm not giving same models, I'm giving different models. The weakest base among the following. The weakest base among the following. The weakest base among the following is option A, it is I minus. Option B, it is F minus. Option C, it is Cl minus. And option D, it is Br minus. So they're asking weakest base among the following. So for identifying the weakest base, you should identify the strongest acid. Strongest acid. So among the strongest acid among the following, we have to identify. So that will fetch you the answer. The strongest acid among the following is, for example, now here, in case how we got this Hi minus means, suppose consider 4 acids. So I'm writing the solution in blue pen. For this solution, you can take hydrogen iodide, first case. Second case, it is hydrogen fluoride. Third case, it is hydrogen chloride. And fourth case, it is hydrogen bromide. Among the following, which is the weakest base? Strongest acid becomes weakest base. So strongest acid is hydrogen iodide. Strongest acid is hydrogen iodide. Its conjugate base will be weak. So what is the conjugate base of hydrogen iodide? Conjugate base of hydrogen iodide means remove H plus ion. So it becomes minus H plus. So again, I'll write here clearly so that you can understand better. So simply I'll write here the conjugate base of hydrogen iodide is Hi minus H plus, because to get conjugate base we have to add and subtract H plus, so it becomes I minus. So among the acids which are as strongest acid becomes weakest base. Since hydrogen iodide is strongest acid among hydroacids of halogens, since hydrogen iodide is strongest acid among hydroacids of halogens, so strongest acid its conjugate base will be weak. I write here strong acid for strong acids its conjugate base is weak. Its conjugate base is weak. So this statement is very important. So for strong acids, its conjugate base is weak. So 100% the answer is option A. That is iodine minus is the answer. Because hydrogen iodide is the strongest acid and its conjugate base becomes I minus. For hydrogen fluoride, its conjugate base becomes F minus. For hydrogen chloride, its conjugate base becomes Cl minus. And for hydrogen bromide, its conjugate base becomes Br minus. Among the hydroacids of halogens, these are called hydroacids of halogens. Hydrogen iodide is the strongest acid, as we already know. Next, question number 6. So please note down this sentence. I will give time for you to note down. Please note down this sentence. For strong acids, its conjugate base is always weak. And among the hydroacids of halogens, hydrogen iodide is the strongest acid. That's why I have selected this. Next question. Question number 6. Like these questions are very, very important. So please note down. Next, based on Lewis theory, which of the following which of the following is a Lewis base? Option A, BCl3. Option B, CH4. Option C is ammonia. And option D, it is nitric acid. So answer for this, you already know, is it's very, very easy. Ammonia. What are Lewis bases? Lewis bases are nothing but what? The compounds which contain lone pair of electrons. The compounds which contain lone pair of electrons. Lone pair of electrons are called Lewis acids. Sorry, Lewis bases. So answer is ammonia, because ammonia contains nitrogen contains one lone pair. Here no lone pairs. Here also zero lone pairs, and here also zero lone pairs. So no lone pairs. And BCl3 is electron deficient compound. Electron deficient compound. So in this case, BCl3 is Lewis acid. BCl3 is Lewis acid because it is electron deficient compound. Because since it is electron deficient compound. And nitric acid is also called as Lewis acid. Water is nothing but neutral one. Sorry, methane is neutral one. So like these questions you will get in the examination. So you should know the definition of Lewis acids and bases. Very, very important. Next question. Question number 7. Now we are going to discuss. Which are the following? Which of the following is strong Lewis acid? Option A, it is K plus. Option B, it is Ca plus 2. Option C, it is Al plus 3. And option D, it is all. So see the question, which of the following is a strong Lewis acid? Option A, it is K plus. Option B, it is Ca plus 2. Option C, it is Al plus 3. So now we are going to discuss this answer. So please note down this sentence. So solution for this. Cations readily accept electron pairs. Readily accept electron pairs. As cations readily electron pairs, they are said to be Lewis acids. They are called Lewis acids. So here all are Lewis acids, but in this strongest Lewis acid becomes strongest Lewis acid. Strong Lewis acid is the cations with more charge. The cations with more charge are strong Lewis acids. The cations with more charge are strong Lewis acids. So please note down this sentence. Strong Lewis acids, the cations are nothing but the cations with more charge are called strong Lewis acids. So answer is third option, that is Al plus 3, because its charge is plus 3. And calcium it is plus 2 and potassium it is plus 1. So aluminum plus 3 is the answer. Like these different types of questions you'll get in the entrance exams, even though they are very small, but you need to identify the things easily. Next question. Question number 8. if HCl is added to pure water at 25 degrees C, 25 degrees C, the ionic product of water will be the ionic product of water will be option A, it is greater than 10 to the power of minus 14. Option B, it is less than 10 to the power of minus 14. Option C, it is 10 to the power of equal to 10 to the power of minus 14. And option D, it is greater than 10 to the power of minus 10. 10 to the power of minus 10. So for this, the solution is, so if HCl is, again I'm repeating the question, if HCl is added to pure water at 25 degrees C, the ionic product of water will become greater than 10 to the power of minus 14, less than 10 to the power of minus 14, and equal to 10 to the power of minus 14, and greater than 10 to the power of minus 10. So it is equal to 10 to the power of minus 14, because already you know ionic product of water becomes is equal to concentration of H plus into OH minus at 298 kelvins. Concentration of H plus becomes concentration of OH minus, which is equal to 10 to the power of minus 7 moles per liter. So by the addition of water, it will not affect the ionic product of water. So ionic product of water becomes, by addition of HCl, there is no effect on ionic product of water. So it is equal to 1 into 10 to the power of minus 14. So answer is C. Very, very important. So this question is very, very important. Like these questions you may expect for NEET level. Next question. Question number 9. So please note down these questions. You may not find these questions anywhere. In the reactions SnCl2, that is tin chloride, plus 2Cl minus, 2 moles of chlorine gives rise to SnCl4 plus 2 electrons. SnCl4 plus 2 electrons. The Lewis acid is, the Lewis acid is option A, it is equal to SnCl is the first option. Second option, SnCl3, SnCl3. Third option, SnCl4, SnCl2. And fourth option, tin stannic chloride, stannic chloride. So answer for this, I'm giving again here. So solution, you can see here, what are Lewis acids? Lewis acids are those which can accept lone pair of electrons. Which can accept a lone pair of electrons are called Lewis acids. So straight away the answer will become, so in this case, which is accepting lone pair of electrons, because chlorine is having minus electrons. So it is readily accepting lone pair of electrons, then only it can form SnCl4. So here in this case, since SnCl2 is accepting lone pair of electrons from Cl minus, because SnCl2 dissociates to form Sn plus 2 and 2Cl minus. So naturally this Cl minus will go to Cl4. So SnCl2 is the answer. So answer is third option. And cations will accept lone pair of electrons as cations are Lewis acids. So SnCl2 is accepting lone pair of electrons from Cl minus. So answer is only SnCl2. Very, very important like these questions. So please note down. Next question number 10 we'll discuss. Meanwhile, you write down the question in your classwork. Next question. So I hope you have noted it. So I'm proceeding to next question, question number 10. So all these different models giving these are only basic levels. Next we'll give for high level also. Ostwald dilution law. Ostwald dilution law is applicable to option A, weak electrolytes, weak electrolytes. Option B, strong electrolytes. Option C, non-electrolytes. And option D, all types of electrolytes. All types of electrolytes. So answer for this, as you already know, what is Ostwald dilution law? For weak electrolytes on dilution, the concentration is being increased. So we can say answer is first option, that is weak electrolytes. For the statement, so if a statement of, for this I'm giving hint, refer to the statement of Ostwald's dilution law. Ostwald's dilution law. Next question number 11. In this only I'll try to write. Question number 11. So please note down. Which pair will show common ion effect? Very, very important. Which pair will show common ion effect? Option A, silver nitrate plus KNNO3, silver nitrate plus potassium nitrate. Option B, sodium chloride plus HCl. Option C, ammonium hydroxide plus ammonium chloride. Ammonium hydroxide plus ammonium chloride. Option D, barium chloride plus barium nitrate. Barium chloride plus barium nitrate. Barium nitrate. So let us see the answer for this. So what is common ion effect? So in first case we have nitrate ion. So that is common. Second case we have Cl minus H and HCl minus. That is also common. Third case we have ammonium ions and ammonium ions. And fourth case we have barium ions and barium ions. So this will form, this will form. And here we have Cl minus and Cl minus. And in the first case we have nitrate ions and nitrate ions. And third case we have ammonium ions and ammonium ions. These are the common ions. but which pair will show common ion effect is most important. So for this, to exhibit common ion effect, I'll write the solution here. To show common ion effect, there should be weak electrolytes. Only weak electrolytes will be shown by common ion effect. Weak electrolytes only. So whichever is having weak electrolyte combination, that is answer. So answer is C. Answer is what? C. Common ion effect will be shown only by weak electrolytes. It's not shown by strong electrolytes. So that's why answer is C. Next question. So in this case, what is the weak electrolytes? Potassium nitrate is a strong electrolyte. Sodium chloride is a strong electrolyte. HCl is a strong electrolyte. Ammonium hydroxide, ammonium chloride is weak electrolytes. And barium chloride, barium nitrate is also strong electrolytes. So that's why to show common ion effect, weak electrolytes must be present. And the weak electrolytes in this case are ammonium hydroxide and ammonium chloride. That's why they framed all common ions in each and every case. So in that, which is the right answer? Answer is third option. So like these tricky questions will be given in the examination. So please note down. Next question. So since we have done so many important models, in the next session we'll do questions based on dissociation constant also. So with this, I'm ending this session. So please follow the instructions carefully and everything will be easy. Thank you all.